You've probably seen it, even if you didn't know what you were looking at. If you're old enough to remember televisions with antennas, you've seen the static. The fuzzy, snowy screen between channels, it came with a sound, a persistent hiss. We thought of it as just nothing, the absence of a signal. But it wasn't nothing. A tiny fraction of that static, about 1% of it, was something incredible. It was the oldest light in the universe. It was the afterglow of the Big Bang. We call it the cosmic microwave background, or the CMB. And calling it an echo is a good way to think about it, but it's not a sound echo. It's a light echo. It's a fossil, a baby picture of the universe, and it's all around us all the time. To understand how we see it, how we here this echo, we need to go back, way back. Back to the very beginning. Imagine the universe when it was just a few minutes old. It wasn't anything like it is today. There were no stars, no galaxies, not even any atoms. It was just a hot, dense, soupy fog. It was a plasma, a seething mix of fundamental particles. Protons, neutrons, and electrons were flying around, zipping past each other at incredible speeds. And there were photons. Photons are particles of light. In this early universe, the photons couldn't get very far. The universe was completely opaque. Think of it like a fog, so thick you can't see your hand in front of your face. Why was it so foggy? Because of all the free, roaming electrons. Photons, the particles of light, have a hard time moving when there are lots of free electrons around. A photon would start to travel and then slam into an electron. It would get bounced off in a new direction, only to hit another electron and another. It was like a pinball machine. Light was trapped. It couldn't travel in a straight line. So, if you were somehow able to exist back then, you wouldn't have been able to see anything. The entire universe was a blinding, uniform glow, like being inside the sun. This hot plasma wasn't perfectly still either. It was churning and vibrating. The forces of gravity and pressure were in a constant tug of war. The gravity would pull particles together, making a region slightly denser, but as it got denser, it got hotter, and the pressure would push everything apart again. This created massive waves rippling through the plasma. These were literally sound waves. Giant, universe-spanning sound waves. This is the sound part of the echo. The early universe was ringing like a bell. Now, at the same time, the universe was doing something else. It was expanding, and as it expanded, it cooled down. This is a fundamental rule. When you expand a gas, it cools. The universe was no different. For about 380,000 years, it kept expanding and cooling. Then, it reached a magic temperature. It cooled to about 3,000 degrees Celsius, roughly half the temperature of the surface of our sun. This temperature was a tipping point. It was finally cool enough for things to calm down. The protons, which have a positive charge, and the electrons, which have a negative charge, were finally slow enough to grab onto each other. They combined to form the first stable neutral atoms, mostly hydrogen and a little bit of helium. This event is called recombination, and it changed everything. Suddenly, all those free electrons that were scattering the light were gone. They were now bound up inside atoms. The fog cleared. In an instant, the entire universe went from being opaque to being transparent. And the photons, the light particles that had been trapped for 380,000 years, were finally free. They burst forth in every direction and began to travel in straight lines, unimpeded across the cosmos. This moment is what we call the surface of last scattering. It's not a physical surface you could touch. It's a moment in time, it's the moment the universe became see-through. The light released at that moment is the cosmic microwave background. It is the very first light that was ever able to travel freely. It's the oldest light we can possibly see. We can't see light from before this time because the universe was a foggy plasma. When we look at the CMB, we are looking as far back in time as it is physically possible to see with light. We are looking at the glowing wall of the infant universe. So, this light was released 13.8 billion years ago. It was very hot and bright, like the light from a dull reddish star. But if that's true, why isn't the night sky glowing? Why don't we see this ancient light everywhere? Well, we do. It's just not visible light anymore. Remember, the universe has been expanding this whole time. For 13.8 billion years, it has been stretching. And as space itself stretches, it stretches everything in it. This includes the waves of light that have been traveling through it since that first moment of transparency. Think of a light wave like a drawing on a rubber band. If you stretch the rubber band, the wave you drew on it also gets stretched out. Its wavelength gets longer. For light, a longer wavelength means less energy. Red light has a longer wavelength than blue light. But what happens if you keep stretching it? The wavelength gets longer and longer, moving past red into infrared and then into the microwave part of the spectrum. That's exactly what happened to the first light. It started as hot, visible light. But over 13.8 billion years of cosmic expansion, its wavelengths have been stretched by a factor of about 1,100. It has been stretched so much that it is no longer visible light. It is now in the microwave range of the electromagnetic spectrum. It's a very low energy, very cold light. That's why we call it the cosmic microwave background. It's cosmic because it comes from the cosmos. It's microwave because its light has been stretched into that part of the spectrum. And it's a background because it's everywhere. No matter where you point a special kind of telescope, a microwave telescope, you will see it. It comes from every direction in the sky with almost the same intensity. So, how do we actually find this? The discovery was a complete accident. In the mid-1960s, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey. They were using a big horn-shaped antenna. It was designed to detect radio waves bounced off satellites. But they had a problem. They kept detecting a faint, persistent hiss, a background noise that wouldn't go away. They tried everything to get rid of it. They thought it was an equipment malfunction. They rewired things. They checked all their systems. They pointed the antenna at New York City to see if it was urban interference. The hiss was still there. They pointed it at a different part of the sky. The hiss was still there. It was the same no matter where they pointed the antenna, day or night, all year round. They even noticed a pair of pigeons had been roosting in the antenna, leaving behind what they delicately called a white dielectric material. They thought maybe the pigeon droppings were causing the noise, so they cleaned the antenna thoroughly. The pigeons came back. They trapped the pigeons and mailed them far away. The pigeons, being pigeons, came back again. They finally took more permanent measures to remove the birds, but the hiss remained. They were stumped. This signal was real. It was coming from the sky, from everywhere, equally. Meanwhile, just down the road at Princeton University, a team of physicists led by Robert Dicke was working on a theory. They had independently calculated that if the Big Bang had happened, there should be a leftover glow from the hot early universe. And because of the expansion of the universe, this glow would now be very cold, just a few degrees above absolute zero. It would be detectable as microwaves. They were literally building an experiment to go look for it. Someone told Penzias and Wilson about the Princeton group. A phone call was made. The two groups met. As the Princeton team described the ancient glow they were searching for, Penzias and Wilson realized that's what they had been seeing all along. The annoying hiss in their antenna wasn't noise. It was the echo of creation. Penzias and Wilson won the Nobel Prize in 1978 for their discovery. It was one of the most important pieces of evidence for the Big Bang theory. It turned the Big Bang from a fringe idea into the mainstream, accepted model of our universe. But the story doesn't end there. Just knowing the echo exists is one thing. Listening to what it's telling us is another. The first thing the CMB told us is that the Big Bang model is right. The theory predicted a uniform background glow at a certain temperature. And that's exactly what we found. The temperature of the CMB is incredibly uniform. It's about 2.725 Kelvin, which is just 2.725 degrees Celsius above absolute zero, the coldest possible temperature. That's incredibly cold, and it's almost exactly the same temperature everywhere you look in the sky. This incredible uniformity was actually a bit of a puzzle. How could two opposite sides of the universe, which have never been in contact with each other, be the exact same temperature? This led to the idea of inflation, a period of ultra-rapid expansion in the first fraction of a second after the Big Bang. Inflation would have stretched a tiny, uniform patch of the universe to an enormous size, explaining why the universe we see today is so smooth. But the most important secrets of the CMB are not in its uniformity. They are in its tiny, tiny imperfections. When we built better instruments to look at the CMB, we found that it wasn't perfectly smooth. There are minuscule temperature variations, tiny spots that are slightly hotter or slightly cooler than the average. These differences are incredibly small, on the order of 1 part in 100,000. It's like measuring the surface of a giant billiard ball and finding bumps that are smaller than the width of a human hair. To map these tiny fluctuations, NASA launched a satellite called the Cosmic Background Explorer, or COBE, in 1989. COBE gave us our first blurry map of these temperature spots. It was a stunning confirmation. The imperfections were real. The scientists who led the COBE project also won a Nobel Prize. But what are these spots? What do they mean? They are the fossilized imprints of those sound waves that were rippling through the early universe plasma. The slightly hotter, redder spots on the map are where the plasma was slightly denser. Gravity was winning the tug of war there. The slightly cooler, bluer spots are where the plasma was slightly less dense, where the pressure was pushing things apart. These tiny fluctuations are everything. They are the seeds of all the structure in the universe today. Think about it. The universe back then was almost perfectly smooth. If it had been perfectly smooth, nothing would have ever formed. There would be no clumps of matter. But it wasn't perfect. There were these tiny, dense spots. A spot that was 1/10,000th of a percent denser than its surroundings had 1/10,000th of a percent more gravity. That's not much. But over billions of years, that tiny extra gravitational pull makes a huge difference. That slightly denser spot would pull in more matter from around it. As it pulled in more matter, its gravity would get stronger, allowing it to pull in even more matter. It's a runaway effect. Over hundreds of millions of years, these tiny seeds grew. They became the first stars and the first small galaxies. Those galaxies then merged and grew into the giant spiral and elliptical galaxies we see today, including our own Milky Way. Every star, every galaxy, every cluster of galaxies we see in the universe today can be traced back to one of those tiny little hot or cold spots in the cosmic microwave background. When you look at a map of the CMB, you are looking at the blueprint for the cosmos. You are seeing the initial conditions of the universe, the starting pattern from which everything else emerged. After COBE, we sent up better satellites to get a clearer picture. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WAP. The WMAP gave us a much sharper image of the CMB. The details it revealed were incredible. By analyzing the precise size and distribution of the hot and cold spots, scientists could figure out amazing things about our universe. WMAP's data helped us pin down the age of the universe to 13.77 billion years with incredible accuracy. It told us what the universe is made of. It confirmed that the ordinary matter we see and interact with, the stuff that makes up stars, planets, and us, only accounts for about 5% of the total stuff in the universe. About 27% is a mysterious, invisible substance called dark matter, which provides the extra gravity needed to hold galaxies together. And the remaining 68% is an even more mysterious force called dark energy, which is causing the expansion of the universe to accelerate. And WMAP also helped us determine the shape of the universe. It turns out the universe is flat. This doesn't mean it's two-dimensional. It means that on the largest scales, it obeys the rules of ordinary Euclidean geometry. Parallel lines stay parallel forever. The angles of a triangle add up to 180 degrees. If the universe were curved, these rules wouldn't hold true. The pattern of the spots on the CMB is sensitive to the geometry of spacetime, and the pattern we see corresponds to a flat universe. After WMAP came the European Space Agency's Planck satellite, launched in 2009. Planck gave us the most detailed, highest resolution map of the CMB ever made. It refined the numbers from WMAP, giving us an even more precise recipe for the universe. It confirmed the model of inflation and provided data so precise that it has become the gold standard for cosmology. The standard model of cosmology we have today, which tells us the age, composition, and history of our universe, is built largely on the foundation of what Planck taught us by looking at this ancient light. So, how do we hear the echo of the Big Bang? We don't hear it with our ears. We see it with our telescopes. We start by building extremely sensitive radio telescopes like the ones on the WMAP and Planck satellites. These telescopes have to be cooled down to near absolute zero. Otherwise, the heat from the instrument itself would swamp the faint microwave signal from space. We point these telescopes at the sky and collect the microwave light. We then have to carefully filter out all the other sources of microwaves. Our own galaxy, the Milky Way, produces a lot of microwave light from dust and gas. We have to subtract that. The sun, other stars, and other galaxies also produce microwaves. We have to remove all of that foreground noise. What's left after all that cleaning is the CMB. A faint, ancient glow coming from every direction. We then turn that data into a map. We use color to represent the tiny temperature differences. We assign red to the slightly hotter spots and blue to the slightly cooler spots. The result is that famous oval-shaped speckled image of the infant universe. Looking at that map is like being a cosmic archaeologist. We are studying the oldest artifact in existence. Every spot and squiggle on that map tells a story. The size of the spots tells us about the geometry of space. The distribution of the spots tells us about the battle between gravity and pressure in the early universe. The subtle patterns in the light's polarization, the direction the light waves are oriented, you can even tell us about the very first moments of inflation, a fraction of a second after the Big Bang. This ancient light, this echo, has traveled across the entire observable universe for 13.8 billion years to reach us. It's not something that happened long ago and is now gone. It's here right now. The photons that make up the CMB are streaming through your body as you read this. Billions of them, every second. They have been traveling since the universe was a baby, and their journey is finally ending by hitting the Earth, or our satellites, or you. The next time you think about the vastness of space and time, remember this echo. It's the most direct connection we have to our own origin story. It's not just a scientific curiosity. It's the remnant of the fire of creation, the faint, cold whisper of the Big Bang, still ringing through the cosmos, telling us where we came from. We just had to learn how to listen.